Hello everybody and welcome back. Root Beer here. We're going to be looking at question number 22 on the 2003 Fermat paper, but before we do that I'd just like to address question 21. So I did question 21 in the last video if you watched it, and as I was looking at this sequence I said this isn't a sequence we really know. If this term is even, you get the next term by having it, and if the term is odd then you get the next term by doing 3 times the term plus 1. And we just looked at that, and eventually it sort of spiraled down into going 4, 2, 1, 4, 2, 1 over and over again. And as I was talking about it, I mentioned that the term Collat's conjecture just sort of popped into my head. And this is indeed correct. Collat's is, I think, C-O-L-L-A-T-Z, so you can look it up if you want. But Collat's conjecture, if you type it into Google and you spell it wrong, maybe I spelled it wrong, it'll typically correct. And basically the conjecture is no matter what number we start with, in question 21 we started with 6, but no matter what number we start with, eventually you'll hit 1 and then go 4, 2, 1, 4, 2, 1. That's the conjecture. We don't know if it's true or not. Just with this sequence that you can list out quite easily, it's instructions. And so that's something, if you want to, by all means take a look at it, see if you can prove that no matter what number you start with, you get all the way down to 1. At one point, I think there was a $500 prize offered if you could prove it. So that's still something to be interested in. I don't know if it's still $500 right now. But Collat's conjecture, quite interesting. But let's put that aside. That's for you guys to go and take and look at on your own if you're interested in. Let's look at question 22, which is the one we're going to be doing for this video. So, question 22, Pentagon ABCD is such that all 5 diagonals, AC, BD, CE, DA, and EB, so every other point, I guess, lie entirely within the pentagon. And I think this is some sort of convexity condition. So it should sort of look a little like a regular pentagon. If the area of each of the triangles, ABC, BCD, CDE, DEA, and EAB, so 3 points that are in a row, in sequence around the pentagon, the area of each of those triangles is equal to 1. The area of the pentagon, ABCDE, is closest to, and then we have some options that basically only differ by a couple hundredths. So we're going to have to sort of be precise. So this question where it's saying is closest to, I'm immediately thinking I'm probably going to have to reach for my calculator because it'll probably be some expression. I'll need to evaluate it and then see which number it rounds closest to, I guess. Okay, but let's get a picture to get an idea of what's going on in this question, because right now I don't really have a plan of attack here. So we have a pentagon, and mine will look a little regular-ish. I'll try and deregularize it. So we have A, B, C, D, and E. Okay. And we're told, let's use yellow here, that each of these diagonals is inside our pentagon. Okay, so we've already drawn something that's sort of correct. And then it said triangle ABC, so this one here, we know has an area of 1. And then BCD has an area of 1. And so everything that's sort of cut off by these diagonals, which we've mentioned lie inside the pentagon, gives us 1. So we have a whole bunch of them. Obviously, there's some overlaps, so we can't just add them all up. And in fact, there's even this space here in the middle that isn't accounted for by any of them. Okay. So what can we do? They don't give me any other information, do they? Pentagon, 5 diagonals lie entirely within the pentagon. Area of the triangle is equal to 1. Area of the pentagon is closest to. So it'd be really nice if all these triangles here were congruent, because then, of course, if one of them is equal to 1, they're all equal to 1. And that would happen if we had a regular pentagon. So if we happen to have, and this is my attempt at a regular pentagon. If we had a regular pentagon, then each of these triangles would be the same. And so with a regular pentagon, ABC is the exact same triangle as BCD. They're just rotated and that sort of thing. And so as long as you make it big enough, as long as you make the side length wide enough, you can ensure that one of them, and therefore all of them, are equal to 1. And with a regular pentagon, obviously the diagonals lie inside. So that's one way to do this question. To my knowledge, they try and shy away from methods like that when they're explaining the solutions. I don't know. Maybe they did for some reason list it in this time. Somebody who's read the solutions might want to go ahead and tell me. But typically they shy away from this because we're making extra assumptions. We're saying, oh, it's regular. And if you were to do this on a written contest, and I know the Fermat is not a written contest, it's a multiple choice contest, so this is a sneaky way to do it. But if this were a written contest like the 2003 Hypatia, where you have to explain everything, where you have to write down your answers, or like the Euclid, where you can earn scholarships and stuff, if it's a written question, you can't make other assumptions, because then you're making the problem easier than what was asked. Okay, so you can't just say, oh, it should be regular. If you think it's regular, prove that it's regular. But you can't say, oh, it works in this case with this regular triangle, and I get this area, therefore it works in all of them. You can't do that on a written question because you need to justify everything. But on a multiple choice question, there's only one correct answer. We already know that for a fact. Okay, so what we can do is we can say, the way they phrase the question, any pentagon which satisfies having all 5 diagonals lie entirely within the pentagon and each of the areas of these triangles equal to 1, as long as we can draw a pentagon that satisfies that, then it has to have the same area as any other pentagon that satisfies them. That's the way they've phrased the question. We can find one pentagon that works and find its area, then every pentagon should be that area. Otherwise, why couldn't I draw this pentagon and get D as my answer, and then somebody else could turn around and draw, this pentagon and B is their answer? It wouldn't work, and it wouldn't work in a multiple choice setting. So it's sort of a sneaky cheat that we can do. And we can say, well, a regular pentagon satisfies all those diagonals being in there, and as long as I make the regular pentagon big enough, all those triangles will have an area equal to 1, and regular pentagons are a lot easier to work with. Okay? Now that's a sneaky cheat. I don't think it'll be in their solutions, but it's something that you are able to do on a multiple choice contest, not a written one. So I'm going to try and find a solution otherwise. But thinking about pentagons, and in particular regular pentagons, my mind automatically starts going to the golden ratio, which is root 5 plus 1 over 2. This is just an experience thing I'm sharing with you. I see pentagons, I tend to think golden ratio. They're sort of connected in my head. And the golden ratio, root 5 plus 1 over 2, when you work it out, is 1.618033989 or something like that. And so my guess would be that if we just go back to my picture here, my guess would be if I do something like take a regular pentagon, or indeed any of the pentagons that satisfy this, if I were to slice it this wise and this wise, I know this is 1, I know this is 1. My guess would be, because this guy looks bigger than either of those, my guess is that this is 1.618033989 or something like that. I think it's root 5 plus 1 over 2. Just gut reaction, thinking regular pentagons work, and just thinking about pentagons, in which case our answer would be 3.618033989. And then it would round to 3.62, and so that would give us an answer of A. But that is purely a guess. I have no math to back that up. I'm going to try and find some math to back this up. So if I tried to do this, if I tried to use this method, obviously these two triangles here, if I use ABC and DEA, those are equal to 1, and so I just need to figure out this sort of blue guy here. I have a base for him right here. What if I drop a perpendicular? If I knew that altitude, and if I knew this base, and so that's actually a lot of extra information I would need. Well, I'll tell you what, this triangle here, this base here, is the base of this triangle and this triangle. Now both of those are equal to an area of 1. And since they have the same base and they have the same area, they should have the same height. So if I just extend DC, should have the same height h, but now I'm introducing yet another variable because I got this base here, these heights, and sort of this height, which we'll call A for altitude. I think I'm adding in too much information here. Oh, but that means that E and B are both the same distance away from the extended line DC. So let's see if I can write this up a little better. I'm not going to write it up super formal because, as I've already said, this isn't the Hypatia. So I don't really need to justify it a whole lot, but I'd like to be able to justify it a little bit to you guys. If I pick a side length like DC and extend it, I know that BCD and ECD both have an area of 1. So I could call this, I don't know, height for BCD, and I could call this distance here height for CDE. And this guy here, CD, is the base. It's the base of both triangles. So 1 is 1/2 base times height, but that's also, or I guess I should write it this way. The area of BCD is 1/2 base times height, which we know is 1, but we also know that that's the area of CDE, which is 1/2 base times height. And when we do all that, we realize that both of these heights are the same. So now, if I add in BE, which I admit isn't exactly BE, he's got to be at a fixed height is always the same distance away from CD. And another way to say that is they are parallel. Now this argument doesn't just work because I chose CD and then BE. This should work for every single, if I pick a side like BC, I should be able to get the same thing. A diagonal AD will be parallel to BC. So our choice of sides was arbitrary. So I know that AB is parallel to CE. And I know that BC is parallel to AD. And I know that CD is parallel to BE. And I know that DE is parallel to AC. And I know that AE is parallel to BD. Okay? This is just doing the exact same construction that I did, but doing it at any of the sides, just rotating this pentagon. I wonder if that's enough to prove it's regular. I'm not sure, but it does mean that we can just sort of summarize this as a little bit of a picture here. If I add in this one, he's got to be parallel to this guy. And if I add in this one here, got to be parallel to this guy. Use orange. That would be parallel to this one. How about some green? So this is sort of what I'm expressing here. I have a whole whack of parallel lines. Does that help me? Have I just drawn a very colorful picture for something that's leading me to a dead end? I actually don't know. I'm having trouble proceeding with this one. And so my advice, if you were in a similar situation, not necessarily with a pentagon-based question, but I'm sort of spinning my wheels in my head trying to figure out where to go next. I would recommend that, since this is question 22, try 23, 24, and 25. There are other questions that might be easier for you. There might be questions that are easier for me. And, if I had the time, I'd probably pause this video, cleverly edit it or something, and go ahead and try 23, 24, 25. But I have quite a bit of time here, because I'm not actually writing a contest. So I'm going to sit and think about this again for a moment. So what have I done so far? I tried to get this area right here, this light blue shaded area, because I knew that I had ones on either side. And in an attempt to get that, I had this base here, and I got these heights, and I got a parallel thing out of there. But does that help me get this triangle at all? No. But so I have this guy is parallel to this guy, and this one's parallel to this one. And these light yellow ones parallel here. 1, 2, 3, 4. We're missing one diagonal. Only one diagonal hasn't been added to this picture. Let's go with green. So that sort of splits it into this top triangle, which is area of 1, although now I'm adding in different areas to, and then this trapezoid here, which can also be split this way. Oh, this is getting a little messy. I'm going to redraw the picture again and see if anything jumps out at me. Clarity of mind is always a good thing. So what was that one I was trying to do? This guy right here, cut on top, and then I could cut it either way to get this guy right here. Maybe cutting it both ways is somehow the key. Both of those is 1. Oh, we got one here and one here. I'm not using any of my new parallel information. So this guy is parallel to this guy. And I suppose we have some other parallel lines. This one parallel to this one. This one parallel to this one. Oh! I spy with my little eye a parallelogram. Not well drawn, obviously, because it doesn't look too parallel to me, but the math says it should be parallel. Does that help me? So this is a 1. Does that mean this is 1 as well? In which case, then, I also know that this is 1. And then we're just left figuring out this smaller section. It's a diagonal of a parallelogram, so it does cut it. So whatever this area is, it's got to be the same for this area. Sure. So maybe parallel lines is a bit more of a key. So how about we draw it with that in mind? So purple is parallel to purple. And green is parallel to green, and blue is parallel to blue. Okay. So, I know this is 1, and this is 1 because we have a purple-green parallelogram here. That's fine. But I also have a green-purple triangle here, and a green-purple triangle here, and a green-purple triangle here. These guys must all be, I mean, these two here are congruent, but I think this one and this one are similar. Right, this angle here and this angle here have got to be the same, and this angle here and this angle here have got to be the same, so this angle here will be the same. So we have some similar triangles going on. Interesting, interesting. What can I do? I don't know the area of this guy. But I do know that if, say, this had a length of A and this had RA, then this guy would be R squared times the area of this bigger triangle, which is 1. So I'd have an area of R squared at that point. Does that help? So I'd have 1 plus 1 plus R squared, and then these other things out here. But they would both be 1 minus R squared. How many times am I going to have to redraw this picture? That's the real question. How many times am I going to have to draw the pentagon? Take your bets now. This probably would have been a lot easier if I just assumed it was regular, but... So 1, 1. This will be R squared, whatever R tends to be, and this will be 1 minus R squared, and this will be 1 minus R squared. Okie dokie. And we'd have to have a length here of A, and then this would have to be RA. So as long as I can figure out the ratio of the two blue lines, I should get an answer of 1 plus 1 plus 1 plus 1, 4, minus 2R squared plus R squared. So that'd be 4 minus R squared. Well, at least that's a little beneficial. And I'll tell you why for a couple of reasons. One, we've got 4 minus something. So our answer, and that R specifically, it's got to be less than 1. Otherwise, the diagonal would be smaller than the line, than the side that it's parallel to. So R is probably less than 1. R squared is less than 1. So we've got 4 minus something less than 1. That means we're in the 3-point-somethings. Okay? So I'm actually pretty optimistic at this point because I think I've stumbled onto something good. The question is, how big is R? You know, if R is 0.9, then R squared should be about 0.81, and we're 4 minus 8.1, and that's, then we're at 3.1 something. Or maybe R is really small. Maybe R is 0.2, in which case then we're looking at 0.04, and it's closer to 3.96 or something like that. Okay? Looking at our answers might give us a little bit of a key. So 3.62, 3.64, so R squared should be around 0.3, maybe it's 0.36, and then R is 0.6. And so maybe B should be our answer. But we're on a hunt. We're going to figure some of that stuff out. Just need to work out exactly what R is. Well, I only see R in 2 places here. And get your counters ready because we're drawing the pentagon again. A little bigger this time. So I see R in 2 places. Oh, jeez. I see R in 2 places here. And we've got these ones here, thanks to the parallelogram. And then I've got 1 minus R squared and R squared. And we'll just leave that there. I mean, there's a 1 minus R squared over here. But inside this triangle is the only place I have So, what can we do? So this is RA, and this guy up here is A. I'd really like to get RA. I don't think dropping this height here will help me. Because then I'd have some sort of RH. And that, I don't think that's going to go anywhere. I have two triangles, and they share a common line here. What if I just took this guy and rotated it? So it sort of looks like the top half there. And I got this line headed out in this direction to go meet the rest of the pentagon. I got r squared here, and I've got 1 minus r squared here. And they both share this common line. This would be BD. And C is up here. So they both have the same height, h here. They only differ in their bases. Their base length here. What can I do? What can I do? So, if this had a base of BB and this had a base of BD, actually just B in lowercase d should do. And then I'd get an area of r squared is equal to 1/2 HD, and 1 minus r squared is equal to 1/2 of HB. So, what does that give me? Well, they sort of have a, if I do 1 minus r squared, yeah, B is going to be the bigger one. 1 minus r squared and r squared here. Well, actually, no, B might not be the bigger one. Depends on the size of r. But I don't like these h's in here. So I'm going to divide through by them. And I should get a ratio of B to D is 1 minus r squared over r squared. Okay. So B is 1 minus r squared over r squared times D. How does that help me? I don't know as it does. B plus D, should that be the same as A? I don't think it should necessarily. I mean, if it were regular, it certainly would, but B plus D, it's a diagonal, sure, but is it necessarily the same length as A? I don't think so. What I'd like to be able to do is say something like B plus D is equal to A, and then maybe I could get a relationship between RA and A. What does B plus D actually look like? 1 minus r squared over r squared D. And then I'll have to do r squareds over r squareds. And so that'll be 1 minus r squared plus r squared. So it'll be 1 over r squared times D is the total length there. I don't see a way to relate that in any good way. Once again, I feel stuck. I thought we were getting somewhere. And now I feel stuck. Okay, hold on. Because if we bring back our colored triangle, yeah, this should work. Although I did use purple already. So we're using red now. We've actually figured out the ratio of this side to this side, and therefore the ratio of the two triangles. So what have we got here? I think I'm going to redraw the picture again. So check off on your bingo cards now. Or I guess not check off, but bubble in your bingo cards now as to how many times I'm going to keep doing this. No, that's not big enough. Okay, so got this one, got this one, and I've got this one. And this is green, and this is green, and we called this D, and we know this is 1 minus r squared over r squared D. And then we had purple originally. I know I just used red a moment ago. And purple, and blue, and blue. So, since they're similar, let's call this point F. Got A, B, C, D, E, and F. By the way, I definitely would have skipped this question and probably wouldn't have had it at the end, just based on my performance right here. If there's a quicker way, I'd love to hear it in the comments. Other than, I think, obviously, the cheat of using... I should stop calling it a cheat. The sneaky tactic of assuming it's regular because the conditions aren't that specific. It's not a cheat to use that to answer a multiple choice question. So I know that triangle BFE is similar to triangle DFC. And so they have a common ratio in their sides. So BF over FD is the same as FE. I guess I should rewrite that. DF, keep the orders proper. Is the same as FE over FC. Is the same as, what's the other one? EB over CD. Yeah. Okay. But I already said, let's assume this is A and this is R. I said this ratio is going to be R. Fine. But now I figure out that BF over FD, that's the B over D that we just had, and that's a ratio of 1 minus R squared over R squared. So that tells me R must be 1 over R squared times R squared. Multiply through, we should get R cubed is the same as 1 minus R squared. Right? It's looking golden ratio-ish, but it seems off for some reason. But if we rearrange, we should get R cubed plus R squared minus 1 is equal to 0. And what can we do from here? I don't know as there is anything I can do from here. I was really expecting a golden ratio at this point. R squared minus R minus 1. Did I do something wrong? Not at all. R squared, 1 minus R squared. That all looks fine. Okay. Is this also an expression that gives me the golden ratio? The golden ratio is supposed to solve this guy. Let's use polynomial division, because I really think it's in there. We had R cubed plus R squared minus 1. We get an R, oops, missing something. Plus 0R minus 1. Okay. So R squared goes into R cubed, exactly R times. We get R squared, R cubed minus R squared minus R. Then I'll have 2R squared plus R minus 1. And that most assuredly does not have a factor of this thing. So, it does not have the golden ratio hidden in it. Okay. Well, that's fine. Oh, okay. No, wait. I suppose I could try and use my calculator to estimate this, but I was pretty darn sure there'd be a golden ratio here, and it's a pentagon. If I assume it's a regular pentagon, then this guy right here, this one here, is the golden ratio times this. So if this were 1, this would be 1.618. 0, whatever. Oh, so this one's the golden ratio. This one's the R that I want to be 1.618. So this is 1 over the golden ratio. Okie dokie. So I had to cheat there for a moment, use the regular triangles. So the way that I'm going through this haphazardly, you might actually want to go and take a look at their past contest, second link in the description, and you can find the solutions to this one. They've got to have a better solution than the one I'm coming up with. But I think R plus 1 is the golden ratio. This is what I think. I want to show that this is true. So I know that R cubed is equal to 1 minus R squared. We just worked that out a moment ago. 1 minus R squared, why that's 1 plus R, which I think is the golden ratio, and then 1 minus R. Can this help me in any way? I know that if this is the golden ratio, it satisfies this equation. And so that would be R squared plus 2R plus 1 minus R minus 1 minus 1. And that should be equal to 0. Some of those 1's will cancel out, some of those R's will cancel out. We'll be left with R squared plus R minus 1 is equal to 0. So if this R plus 1 is equal to the golden ratio, then I should be able to get this polynomial divides this polynomial. R cubed plus R squared plus 0R minus 1, and then we should get an R up here. R cubed plus r squared minus r. And then that would give me something that still doesn't give me the answer I want. Well, this is a terrible little pickle. Not entirely sure how to proceed. Well, ultimately I don't need r, I need r squared. Right? So maybe if I solve for everything in terms of r squared, it'll be a little better. Right? Because remember our equation was we need 4 minus r squared. That's what we need there. I thought maybe we could just solve for r, which I maintain should be 1 over the golden ratio, which would be 1.618033989. So it should be 0.618. So, oh, 1 over the golden ratio is the golden ratio minus 1. I already knew that. And I do have this equation correct. This is the one that r should satisfy. My God, this question's taking me a long, long time. But I don't get even polynomial division here. I just need r squared. Incidentally, all this work is pointless now. I really wish I had a quadratic here, not a cubic. And I feel like they think I should have a quadratic, not a cubic, because a cubic is really hard to solve. I can't see any solutions to this particular cubic. Well, unless I say something like r cubed plus r squared is equal to 1, leave it over like that. R squared times 1 plus r is equal to 1. R squared is the same as 1 over 1 plus r. So r squared is the same as 1 over 1 plus r. So what we're looking for instead of 4 minus r squared is 4 minus 1 over 1 plus r. Does this help me? I'm not entirely sure that it does. This shouldn't be that hard. It's question 22 on a Fermat. Well, let's see. R squared is 1 over 1 plus r. R is 1 minus r squared over r squared. So this should be 1 minus 1 over 1 plus r. Somehow I'm just going to get a 1. I'm going to get r equals r, aren't I? So that's equal to 1 plus r over 1 plus r minus 1 over 1 plus r over 1 plus r. Yeah, I'm just going to get an r here. So that's also useless. I know from looking at the pentagon that 1 over r should be, 1 over r should be the golden ratio, right? I don't want to use the regular pentagon, but the regular pentagon does work. Let's see. R is 1 minus r squared over r squared, and that's 1 minus r, 1 plus r, over r squared. And 1 over r, 1 plus r is 1 over r squared. So r is 1 minus r, 1 over r squared, 1 minus r over r to the 4th, and somehow I've just made things worse for myself. Okay, so let's strike that. That didn't work. R is 1 minus r squared over r squared. So r plus 1 should be 1 minus r squared over r squared plus 1 written as r squared over r squared. So that should be 1 over r squared. R plus 1 is equal to 1 over r squared. And that would still get me r cubed plus r squared is equal to 1. So that doesn't help me. I really feel like there should be a golden ratio here, and I'm not seeing one. And I'm also not finding a nice way to write out what r is. I just need r squared. R is 1 minus r squared over r squared, so r squared should be 1 minus r squared over r squared squared. Another way to write that would be 1 minus r squared over r squared times r. We'll see which one's better. That would be 1 minus r squared over r. But if I do it this way, I get 1 minus 2r squared plus r to the 4th all over r to the 4th. Why is this question so hard for me? So I've come to the conclusion that I've made some sort of error somewhere. I have to have. 1 minus r squared there, r squared there. So that means these sides must have a ratio of 1 minus r squared to r squared. And so that must be the same as the ratio of 1 to r. EB over CD, and there it is. There it is, folks. This one on top is A, and this one was RA. So in fact, this ratio is 1 over R. I'm an idiot. I have wasted everyone's time. But now I can proceed. I found my error, and I'm sure this is now a 30-minute video, or something like that, but I found my error, and let's be teacherly and say that that was all for your benefit, and that was all so you can see how to cope when clearly something is wrong. I found my error. It shouldn't have taken that long. This is question 22 on the Fermat 2003. I do apologize. Read their solutions. I'm sure it's much quicker and cleaner. But now we can proceed. 1 minus r squared over r squared is the same as 1 over r. Yeah, I said that triumphantly. I still don't know if I have a solution here. Multiply by r squared on both sides. We should get this. And so, bring the r squared over to both sides. R squared plus r minus 1 is equal to 0. So we have a quadratic, finally. We can use the quadratic formula. R is negative 1 plus or minus square root of 1 squared minus, but the minus signs will cancel, plus 4 all over 2. And that's negative 1 plus or minus square root of 5 all over 2. There's no way r will be negative. So r is equal to root 5 minus 1 over 2. And area of the pentagon, which we knew a long time ago, is 4 minus r squared. So that's 4 minus root 5 minus 1 all over 2. R squared, by the way, is also, r squared is 1 minus r, so I guess we could rewrite this a little bit. It's 4 minus 1 minus r, so that's 4 minus 1 plus r, so that's 3 plus r, and that's 3 plus root 5 minus 1 over 2. I don't know if that's any better. That's 6 over 2 plus root 5 minus 1 over 2. You can tell I'm all excited because I've got an answer finally. 6 minus 1, so that's 5 plus root 5 all over 2. That should be the exact answer. Let's see if that's an answer that we can work with in terms of the solution. And that is about 3.618033989. So that's 3.62. So that's the A that was predicted 2 hours ago whenever I started this thing. I know it's been quite a long time. But that is the answer A that I predicted because I saw that it was pentagons, and I was banging on and on about the golden ratio because I had experience, and all I really needed to do was just to find my error. I jumped the gun when I made that ratio between those similar triangles, and that is what held me up. And again, I apologize. Let's put question 22 behind us and move on to question 23 in the next video. So I'll see you then if you're still even watching at this point. Okay? So long for now.